Okay, so let's start. So let me welcome you all to this lecture 3 out here. Here we last class we learnt about CS amplifiers. We are going to see other amplifiers today. So a quick recap. We did CS amplifier last time. So we saw these two resistors are used to bias this and set the Q point. RD essentially helps in setting the Q point as well as that determines the gain, okay, because RD we are assuming it to be much lesser than R0 and RL, okay. So so then we saw the small signal equivalent out here where we saw the gain is actually GM into VGS into RD parallel to RL into R0. So this was the one of the drawbacks of the CS amplifier, that the gain is proportional to RL, right. So RD determines the gain. So this was one of the drawbacks. Now also when you for your exam right, if your source resistance is given, then obviously this acts like an potential divider. So this VGS is actually a portion of the V signal. So overall gain, so it will be this into RG divided by RG plus R signal, okay. So there will be some drop of gain, so you have to cater for the loss which is happening here also. So that was about CS amplifier. Then we talked about in general how to do a hand calculation of finding out these resistances. I told we need to set this as a VDD by 2, okay. So that is actually okay for when the voltages are high, but for if you are speaking like somebody brought it out in the last class, that in case we are working at lower technology nodes and this voltage is say around only 1 volt, in that case we need to consider the overdrive voltage. If you have to keep this transistor in saturation, so the minimum voltage out here will be overdrive, okay. So this equation gets modified, VDD divided by V overdrive by 2 divided by IDQ. Okay, is this thing clear why this overdrive has come? Initially we told VDD minus 0, now we are catering for V overdrive voltage also, right. So we can do that, but generally we should avoid operating this at close to VDD and 0 swings, okay. Because non-linearity sets in that case, okay. So if you actually require an output voltage from close to 1 volt, 0 to 1 volt, then it is better to go for a higher supply voltage circuit rather than trying to reach close to 1.8 volt. Okay, what happens, you see here the ID, GM is ID, right, and we are assuming the bias current is ID and there is a small change in current, okay. Now but if you are targeting very large swings out here, this ID will change, the gain will change. So the output signal will not be ideally replicating the input signal, because gain is different for different input voltages, right, because the input signal is so high that it is changing the operating point. If it is changing the operating point, the gain will change. So you will find lot of non-linearities coming in. So that way we generally make an amplifier that this voltage is not going close to VDD and 0. In that case we can just neglect this VOV. Is this okay with all of you what I just spoke? Is it understood? Okay, if there is any doubts please ask me.
Sir, once more can you repeat please? I got a little bit issue here.
Yeah, okay, no problem. See, last time when we decided the value of RV, we said for maximum voltage swing we keep it as VDD and 0 and we keep it as 0.9 volt here, right. So we did RD is equal to VDD divided by 2 divided by IDQ, okay, assuming that this is the ideal position, right. But but if you want to be very precise, this transistor has to be in saturation, okay, even when this voltage goes low. So we cannot allow this to come to below VOV. So we insert this VOV overdrive also out here. So RD you can be computed, okay. But another aspect to it is when we are designing a circuit, we should not design a circuit where the output voltage swing is very large and it is close to the VDD voltage. If we do that, what happens is when the input if this input voltage is close, swing is very large, okay, that will change the value of the GM, because now input voltage is large, so ID will be right, it will manipulate the ID, the gain will change, so your input signal will get deteriorated. So generally when an amplifier is made, ID, capital ID, VD should be much greater than the small signal which is there and the small ID. Is it okay? Otherwise there will be linearity issues.
Yes.
Okay. So in that case you can neglect this VOV and follow what was told in the last class. Okay. So
Hello?
that is, yeah, tell me.
Sir, one query. So what you are saying is a V out. So if we have that V2 is 1.8, the V out what we have should not be going to a swing till 1.8 volt.
Yeah, correct. Generally, right, if there is a requirement of say 1 volt output signal, right?
Okay.
Say if I have 1 millivolt here and I want a 1, then I could use 2 stages of amplifier. Okay, first get it to some level out here, and then the second stage I need to use a higher voltage. Okay, so this output voltage swings should not be very close to VDD. That will set in non-linearities. Okay, you understand what non-linearity is?
Yes.
Okay, the gain will not be uniform. Right?
Uniform, yes.
Okay.
Sir, but one question. Then for one particular single stage common source amplifier, how will we determine how much is the VDD we require based on the level of the input signal and the gain required? Yeah,
that because for each requirement, generally if this is the 180 nanometer technology file and 180 is the voltage which is available, right? And your signal levels which requires to be is within say 0.6, 0.8 volt, then we go like this. But if there is a requirement of higher voltage, then you might want to use an different technology device altogether. Right? Okay.
Yeah. Thank you, sir.
Yeah. Power MOSFETs or something which operates at higher voltage. Okay. So, okay. Now then we saw this. Okay. Again is a function of load resistance. That is one issue. High input impedance. Okay, high input impedance is good when this is being driven by another CMOS amplifier. Okay, but if it is being driven by an by an antenna which has got 50 ohms and at higher frequencies, in that case, if the those antennas generally have 50 ohms or low resistance, and this has got high resistance. So at high frequencies, at RF frequencies, that will result in impedance mismatch, and there will be standing waves which will be formed. So that is not desirable. So high input impedance is good as long as this is being driven by another CMOS amplifier. But for certain applications, this is not a good feature. Okay, higher Miller capacitance, which we discussed, this is not very good for high frequency applications. Now this is important. I have a current gain, I have an voltage gain, and I have a power gain for this amplifier, isn't it? Right? Current gain, because there is negligible current here. Okay, there will be high current gain here. Voltage gain will be there, and power gain also will be there. Okay. Now we saw another circuit in which we saw this is not stable with respect to VDD. So we inserted an RS out here. On inserting an RS, we saw that there is a better bias stability, but okay, the drawback is the gain reduces minus RD by RS by putting this RS value. Okay. So then we did this derivation where we considered this body effect also R0. So these kind of making equivalent circuits and these kind of derivations, there are ample examples given in your textbook for various circuits. Okay, so I will suggest you go through all those derivations, because they may I am not covering every circuit which is there in the textbook, but from your examination point of view, just try to analyze those circuits and those derivations. So it will be important in that way. Okay. Now the one thing which we left out in the last class, what is the output resistance when you see from here? Okay, what is the output resistance? If I see here, if I apply a voltage out here, right, there will be there are three currents out here, right? So I write I out is equal to minus GM. What is the voltage out here? It will be I out RS, and VGS, because this is ground here, so VGS will be minus I out RS. So this will become minus GM RS, this current, right? Similarly, VBS, this is also source is at I out RS. So body is in ground, so this also becomes minus GMB I out RS. And what is the current going here? It is V out minus I out RS divided by R0, right? So I multiply by R0 and I write like this, so I get this particular equation. And then since this RS is much lower as compared to R0, this is in kilo ohms, this will be in mega ohms, and this is an approach. So I make an approximation. GM also I am assuming it to be much less, GMB much lesser to GM. So this is the equation finally I get. Okay, so this is an important thing. In fact, it's very important for so when I am putting a source resistance and I am looking from here, right, the actual resistance is R0, which was there initially. Now by putting an RS, now the output resistance will be RS, okay, plus GMR0 also here. So the input impedance increases, output impedance increases significantly. Okay, is this derivation clear to all of you? And this thing is okay with all of you? Yeah, is it okay? If you keep responding, it will be better for me.
Sir, can you explain once again how this single RS was eliminated?
Just because of the values, okay? Assuming that RS is much lower than R0.
Okay.
Okay.
Sir, by without looking at the, I mean, if we don't derive this R out, can we look at the circuit and see what is, I mean, if this the circuit R out of the circuit will increase or decrease?
Yeah, that's what.
By putting
whenever there is a transistor here, okay, it will be R0. This will be there as such. Okay, this gets multiplied by a factor GMR0. Okay.
Yes, sir.
Okay, so this you need to remember. For approximate calculations, R0 will be there. Whatever is there below the transistor will get multiplied by this factor GMR0. Okay.
Okay, sir.
So you need to remember.
So at what point?
Yeah.
So at what point this KCL application was there? Was
here.
applied KCL.
KCL was at this node. I out is coming into, these three currents are going out.
Okay.
Right. Okay. Then we talked about since the gain was less, we put a capacitor out here. So in the AC signal, we got back the gain. Okay, full. So that is what we did, right? So DC operating point remains stable, whereas the AC gain comes back by putting this resistor. This we saw, right? And then we saw with constant current source. Instead of RD, we can put a constant and a current source on the top, right? So this is the resistance of the constant current source. Generally, it is a PMOS, so that will be also R0. So as compared to RD, R0 will be much higher, so we get a much higher gain. So it always makes a sense by putting constant current sources, right? We can also make CS amplifiers with PMOS and putting a constant source at the drain side of the PMOS. Okay, this is another configuration. This is constant active load, right? So the gain is R0 parallel to R1. So we get very, very high gain by doing this, right? And then okay, here while designing the design steps, which we didn't discuss, again same. First we find out IDQ, taking max power constraint and the minimum power constraint, and then we know the gain requirement, right? We know the values of R1 and R2 also, right? Because once ID is decided, R0 will be what? 1 by lambda ID, right? So R0, this gets fixed. Okay, so once these gets fixed, and RL is also known, gain gets fixed, GM gets fixed. If GM gets fixed, right, with GM, you can calculate W by D and W by L for both these transistors, right? Because it's the same current which is flowing. It will be mu P for this, it will be mu N for that, right? And then accordingly, VOV also can be computed. Okay, so that is the only difference while doing hand calculations. Okay, so we find the gain, and from there we compute the W by L ratios and the overdrive voltages. Okay. Now we can have various kinds of loads. Okay, this is a CS amplifier on top. So these are 4 different configurations. You can have more. I have just explained 4 of them here. Here, see, if you this is an NMOS. I am putting this to VDD, this to VDD. So when I look from the bottom, it will offer 1 by GM. Okay, a resistance. Okay, so that is a low resistance, 1 by GM. Okay, but it will be in few kilo ohms. Okay, because this is in milli, this will be a few kilo ohms. It is still better than resistance. Okay, because this gives design flexibility. It is easy to make the headroom out here. So this is one configuration. Or I can give a fixed G out here, right? In that case also, when I am looking from the bottom, okay, because VGS is changing, it is 1 by GM. Okay, this input impedance as seen. Instead of RD, it will be 1 by GM. Instead of RD, it will be 1 by GM for this configuration. Here also, when I look from the bottom, it will be 1 by GM. Okay, if I make this is PMOS, if I make this kind of connection. Here I am giving G. Here, if you see here, VGS is fixed out here, right? So this will be remain in saturation. And when I look from the bottom, it will be R0. Okay, so this is 1 by GM, 1 by GM, 1 by GM. If the gate and the source voltage are fixed, right, and then you are looking from here, then it will be R0. Like so, these are NMOS, PMOS, PMOS. So these are known as active loads. Okay. So where did this 1 by R0? I hope you understand, right? This is VSD, VG is fixed. Okay. Why did this 1 by GM come? Where did this 1 by GM come? So I will do one derivation, and rest of the things you can try it out yourself. See for this particular circuit. Okay. So I make an equivalent circuit. Okay. So gain and drain are shorted there. I am applying a voltage here. So this is GM VGS, GM VBS, and R0. Right. Now if I am trying to apply, so Vx, I am applying KVL. Okay. So this voltage, okay, is equal to this voltage, right? R0 voltage, right? So and VGS is nothing but minus Vx, because gate for small signal I am grounding, I am applying voltage here. So this becomes minus Vx. Similarly, VBS also becomes minus Vx, because I am applying at the source. The body and the gate are grounded. Right. So now if I am applying KCL at this node here, right, this Ix is going inside, right? It is GM Vx. Okay, this is also all the currents which are coming into the node. GM VGS, GMB VBS, and minus Vx R0, because this is ground. So the current coming into the node will become a minus. Okay. Now VGS I substitute as minus X, BS also as minus X. Okay. So I get Ix is equal to GM Vx plus GMB Vx plus Vx into R0. Right. So if I take an Ix there and I bring these three here, so I'll get an 1. So if I consider, this will be 1 by R0. Okay. So since R0 is in mega ohms, I neglect that. And if I consider an GMB also, if I neglect that, I will get as 1 by GM. And if you don't want to neglect this one, it will get 1 by GM plus GMB. Okay. Is this okay? Where did I get this input impedance as looking into this transistor? Is it okay? Anybody?
Sir, how we predicted the direction of the current of R0 as we are taking negative of Vx by R0?
See, we are applying KCL, right? The
KCL,
algebraic sum of all the currents coming into the node is 0. So Ix is here, GM is here, GM. So we have put plus plus, R0 here, right? So current we will add. So it is 0 minus Vs, right? So minus Vx. Is it okay?
Okay, sir. So we are taking the direction of R0 from drain to source, right? It's like this.
No, in this circuit, we are doing for a point A here. we are taking KCL. Okay, all the currents which is coming into A is 0. So drain is 0 here. For AC analysis, here it is 0. Here it is Vx. So the current is negative taken out here. Is it okay with all of you?
Okay.
Okay.
Thank you.
Okay. So this is the kind of resistance it's offered. Okay. Generally, we don't use RD anywhere resistances. We use MOSFETs like this for load. Okay. Where you want high resistance, we will use PMOS like this. Otherwise, if you require just 1 by GM, which is also in kilo ohms range only, you can use these kind of things. Okay. So that is, I have done derivation for 1. You can try out for these also. If you write these equations, you will somewhere, obviously, when you make R0 will be neglected and GMB will be neglected. Okay. So you will get 1 by GM. Okay. So this is known as common gate amplifier. Okay. What is common gate amplifier? Like we said, common source. The source was common to the input and output. Here the gate is common to the input and output. Okay, so you are applying an input signal at the source of the here. So this is a bias. Okay, these resistances are bias resistance, and here you are putting one resistance to set the operating point, and you are applying an source out here, right? And you are also putting one capacitor out here, so that there is an AC ground here. So in the small signal analysis, the gate will be grounded out here. So you need to put a capacitor here, because from here, okay, I don't want in the AC signal R1 and R2. I just want a ground out here. So that is the reason I have put a capacitor out here, and I am taking the output from here. Okay, so this is known as a common gate amplifier. Okay, let's see what are the advantages and disadvantages. Right, and now first of all, we try to find out Vx by Ix. Okay, what is the value? If I put here, what is the input resistance? If you try to find out as looking, right? So same equation, R dx into Ix. Okay, this Vx. Okay, this is actually this voltage. It is R0. Same, right? You are trying to find out RD. This voltage will be RD into Ix plus this voltage across R0, and the voltage across R0 will be Ix is coming from here, right? Some currents are flowing in this branch, so remaining current has to flow here. So Ix minus GM plus this, okay, these two currents. So that will be the voltage across R0. Understood? Vx is equal to sum of the voltage across R0 and RD. So that is what I am doing here. And what is the voltage across R0? Ix is the total current coming from here, out of which there are two different branches out here. So I am putting that voltages here as Vx. Okay. So now Vx by Ix will come out to be R0 divided by this equation. Right. Now if you consider this 1 plus, if you neglect this one, okay, or if I just divide by R0, I will get these values, right? So again, if I neglect R0 and GMB, I will get 1 by GM. That is the impedance as seen into the common gate amplifier, right? So if I keep GM value very large, okay, so the input impedance will be low. So I can, if I keep GM very large, so I can reduce the input impedance, and that will be good for applications like where I have to couple it with an antenna and things like that. Is this advantage of an CG amplifier clear to all of you? Right, it has got a low input impedance. Okay, so if I keep the value of GM very large, okay, so I might have to use a higher currents, biasing currents, or I can use large W by L. By that I can keep this GM value, right, 1 by GM, I can get it close to 50 ohms and things like that, so that I can easily connect an antenna and things like that, okay, of low impedance. Okay, so for RF application, so common gate amplifier can form the first stage of amplification where input impedance needs to be matched. Okay, now what about gain? Okay, now gain is, this is Vx. Okay, now GM into V1 is flowing like this. Okay, that flows through RD also, right? So and GM VBS also is flowing into RD. So the gain will become an RD into GM plus GB. So you will get marginally higher gain than the CS amplifier. Is it okay with all of you? The gain is similar to that of a CS amplifier. Voltage gain. Is it okay with all of you?
Sir, can you explain how gain calculation you have done?
Gain, okay. V out is Ix into RD, right?
Right.
Right. And what is Ix? Ix is this current plus this current, right? GM plus I am neglecting this GM plus GMB of these two currents,
Okay.
right? Into V into Vx. Is it okay?
So, okay, got it.
Okay.
Yeah.
Okay. So a common gate amplifier, there is voltage gain, there is a low input impedance, right? What are the other advantages? High frequency applications. Okay, high frequency applications because there is no Miller effect. Okay, let me go back to this circuit. Here, if you see, the signal is the gate and the source voltage. Is there any voltage gain between this place to this place? There is no voltage gain. Voltage gain is between here and here. So there is no voltage gain from here to here. So the equivalent capacitance, as it is, it will come down. It will not get multiplied by the gain. Okay, is it understood? We saw in the common source amplifier, the issue was the common, if I go here, common source amplifier, here, this CGD, okay, actually the signal from here to here has got gain. Okay, so this CGD will come into the input side in the equivalent circuit as CGD into gain. Okay, so that becomes a large capacitance that will attenuate high frequencies. Here in this particular circuit, right, here between the gate and the source, there is no voltage gain. The voltage gain is between the source and the drain region only. There is no voltage gain between the gate and the source, right? Here like this. Okay, so and hence, whereas this capacitance is as such very low. This is a large capacitance. So if that doesn't get multiplied by the gain, and that is why this doesn't have an issue with high frequency application. Is this aspect clear to all of you?
Yes, sir.
Okay. So so let me before proceeding further, let me show the simulation here itself so that we understand things better. Right, so I have made this CS amplifier. Now I have made a CG amplifier, a same amplifier. I have just put a capacitor in and I have brought the source out here. So 2K, right? So let me run a simulation and plot the AC signal. Okay, so this is the CS amplifier. This is the CG. So what you see in blue is the CG. So you will find a marginally higher gain and higher bandwidth. Okay. So if I do the transient analysis, also. So you see, this is the signal for the CS amplifier, and this is for the CG amplifier. Okay, you can also note that in the CG amplifier, the signal is in sync with the input signal, right? because if the signal out here increases, so there is a phase difference also, right? So you can see that. So this is the advantage of having an CG configuration. Is it okay with all of you? Right? So marginally higher gain and higher frequency. We have seen that. Okay. Okay. Now I have something with the common drain amplifier. Okay. And now what we saw for both the earlier configurations, one of the drawbacks was that here also, okay, the final gain is dependent on the load resistance. Okay, I can't connect whether it be common gate or common source. I cannot connect low load. Okay, but if I want to connect low loads, okay, low loads, then I need to use common drain amplifier. Okay, say because like say what we have our audio devices which operate just in 5 ohms impedance, 16 ohms impedance and all that, right? So you will have in practical applications loads which are very, very low. So in those cases we use something known as common drain amplifier. So this is the configuration, right? You have the input signal being given to the gate, but output instead of from the drain, I am taking it from the source out here, right? So this is RS, this is RL, right? So this is the equivalent circuit. R1, R2 is taken in parallel. So input signal is available here. So these two are in parallel. Okay. So if I try to find out the gain value, now here the V in voltage which I have applied, right? Here V in I am applying, that is VGS plus this V out. Okay, is this equation clear? V in is equal to VGS plus V out. Now this equation is right applicable here. V in is equal to VGS plus V out. Okay, so I write this equation, right? And this is V out. Okay, so if I try to find out the if I V out divide, this is the current which is going to flow in this R out parallel to R0. Okay, this RL dash is parallel of these two resistances, right? RS and RL. RS is the biasing resistance which we put, RL is the load resistance which we put. Okay, so RL parallel to, okay, this should be this should have been RL dash parallel to R0, right? So that is one current, and that is sum of these two currents also, GMVGS minus GMB V out. Okay, so if you try to find out the gain doing a manipulation out here, so you get it this form. Okay, this is a simple equation, KCL equation. Just have a look at it. I will be sharing the PDF also, right? So this is the gain equation which we get. Okay, now if I neglect this particular term, okay, if I neglect this particular term, if I keep GM sufficiently high, okay, so the gain will become GM divided by GM plus MB, which is equivalent to 1. Okay, so the voltage gain is actually close to 1. It will be slightly less than 1. That is actually common sense also. If you directly see here, this is the V in voltage applied here. Okay, a small VGS will be dropped here, and here it will be actually right, V out is equal to V in minus VGS. So the gain is almost the entire input voltage will be available here, right, minus a small drop out here. So the gain is slightly less than 1 for a common drain amplifier. Okay, now can you tell me, okay, the one advantage I can see out here is clearly the gain is not a function of load resistance. Okay, if I keep GM very large, okay, so that is a critical condition. I have to keep GM very large. Okay, then I can even connect low resistances. The gain will be will not be a function of that. Okay, but in this case, why am I calling it as an amplifier? If at all there is no voltage gain, can anybody tell me? It is actually an attenuator, right? But I call it as an amplifier. Yeah, anybody can make it.
Related to current?
Current? Yes.
Current gain.
Current gain. Actually, there is a power gain. Okay. when low output impedance, and that low output impedance will mean that I can connect low node. R out is actually when you look into the it is 1 by GM, okay, or 1 by GM plus GB. So that is the reason I am able to connect a low load. Again, it's not a function of load resistance, and there is no current gain also. There should be current gain. This is current gain is not there for CG amplifier. Okay, is there a current gain for CG amplifier? Because this current is flowing like this, right? The current which is flowing here will flow here, so there is no current gain there in CG amplifier. Whereas in a common drain, I can remove this off. Okay. Right. So there will be power gain. Is it understood? Power gain. Why I say? Let me give an example. Right. Common drain amplifier. Where is it? Okay. Here the voltage is say 1 millivolt. Okay. What will be the current out here? It will be negligible because it is a gate. Whereas here it is 0.9 volt, right? And 0.9 volt by RL, right? So RL is very low, right? So this is V square by R power. R is very great. Here it is V square by R. This RL is very low. So you have power gain, right? Now obviously power gain means where is the additional power coming from? Actually that power is coming from the VDD which you are applying, right? The power is not consumed from the source. The power is consumed from the VDD which is applied here. Okay, is it okay? The voltage remains same. Okay, the additional current is very high, and that current is actually coming from the VDD. So our VDD which we are applying, that is the power source. Okay, so this is amplifying the power, and that is why we call this common drain also as an amplifier. Is it okay with all of you?
Yes, sir.
Yeah. So these are small. Tell
Sir,
me.
in common gate, once again, please explain what is current. Why there is no current gain?
Okay. What is the current out here? Right, if you make an equivalent circuit, right, this, right, so this is the current which goes into the load, right, from here, and it is the same current which is going into the load also.
Yes, sir.
Right, that is why it is almost one current again.
Okay.
Right, this current is going from here, it will go into the load, so it is the same current.
Okay.
So the current gain is approximately 1 there for common gate, and for common drain the voltage gain is approximately 1. Okay. So let me show some simulation before I proceed further. Right, this is our common source amplifier. Okay, I am amplifying the signal here, and then I am using a common drain amplifier. Okay, in the common drain amplifier, instead of using resistances, I have used for biasing also MOSFETs. Okay, in this configuration. So they will so this is actually off, right? Both are off because drain source voltage. So not much current will flow in this particular path. But I can get the desired voltage out here, DC operating, by adjusting the width of these transistors, right? W is a design variable which is available to me. So I can set this value, okay, through simulation, okay, by trying an simulation and try and find out the voltage. If I give a large W here, the voltage will keep dropping. If I keep because the resistance is lesser, right? So you can think it of as a potentiometer, and you can instead of resistances you can use MOSFETs also like this for biasing. Okay, so let me do this simulation.
Here we are using MOSFET for biasing. Right? The bottom NMOS is off.
Top is also off.
Yes, so it will provide very high impedance.
Correct.
And the changing the W, increasing the width will not change the impedance, right?
No, relative to the PMOS. Both are off only, right? So I can.
Why increasing W increases this R out? I mean, R out is 1 by lambda ID when ID is 0 here, right? It is off, cut off.
No, actually you can think it of a sub-threshold in a conduction region, right? There will be some currents in picoampere. So with respect to the PMOS, okay, so this is also off, this is also off. Both are in megaohms. But if you change the relative widths of these two transistors, you can adjust this operating volt. Like I have kept it as 1.18 this operating volt, right? If I want to change that, I can change the width of these transistors. Is it okay?
But sir, in sub-threshold region, like if the current is in picoampere, with process and temperature, this current will change drastically, right?
Which one? These currents?
Yes.
Yeah. See, I have just given an example where you can do that, right? So generally, for all analog circuits, we will learn about current mirrors in the next after differential amplifiers. We use a reference voltage and constant current biasings, okay, to keep it stable.
Okay.
I have just given you one option. Just shown this. I have deliberately put this so that such options are available to you. Okay. Yeah.
Okay, sir. So one more question I have. In the common source amplifier, we are giving a V in as input, right?
Yeah.
So that is getting converted into current.
Correct.
So when we are saying CS has current gain, I mean, how do we what does this mean?
Current gain means what is the current drawn from the source? Okay, it will be
that is zero,
almost zero. So it has got very high current gain. Okay, depends on R1 and R2. Okay, right?
So we can this will be always in picoampere range, right? The gate current.
Yeah, gate current will be. Yeah.
So current gain will be very, I mean, 10 to the power.
Yeah, it will
almost
be very
7 high. Or 8.
Yeah, it can be very high, right? See,
do we use this current gain anywhere?
No, we are this we generally use for boosting up the voltage, giving an high input here.
Okay.
Right? So,
okay.
Now, if I see this is I am plotting the output at VCS, right? I am getting an 14 gain of around 14 out here. 1 millivolt signal is gain. 14 out here. I am using an R is equal to 1000 K, right? Now, suppose if I plot CD also, I am getting slightly lesser than 14. Okay, that is fine. Now, if I change this R load, okay, say to 1K, for example, right? If I do that, so this is 0.8 volt. That means this particular amplifier cannot support low loads. Is it understood? 1K, the signal is gone down, right? It is gone to 0.8 millivolt. So this amplifier cannot support low loads. So whenever I have to drive low loads, okay, I will use one more stage, which is C D, and then here I can connect I have put only 1K here. Sorry, see, already I have put 1K here, right? Even with 1K, if I put 1000K also, gate will be right. So this is not really changing much. If I put even 100 ohms, let me see, right? Still I am getting a good gain out here. Understood what is the application? Right? This is a CS amplifier. This is a CD amplifier. CS amplifier, if I reduce this, if I have to connect a low load, this gain will die down. Okay. So I saw when I putting 1K, it is going, actually the gain is going negative. I am getting 0.8 volt. I am giving 1 volt here. I am getting 0.8 volt. When I am putting instead of 1000K, 1K here, right? Whereas now I am putting 1000K here. I have introduced one more amplifier in between. Here I am giving even 100, right? So from here, from around 14, it has gone to around 9. Okay, there is some drop from here to here, but still I am able to put 100 ohms resistance. So that is important for me. Is it okay? So if you see any amplifier, the final output stage will be a common drain amplifier. Okay, wherever I require. Yeah, tell me.
Hello, sir.
Yeah.
Can we use output of common source directly into the common drain? I mean, without any. Why do we need this C4 and this biasing circuit? I mean, we are getting common mode at 1 volt.
Yeah, yeah. You can.
So can we use directly?
We can do that. We can do that, right? Because
is there any drawback of that?
No. There is no drawback. In fact, you should try and do that. If you are able to maintain the DC operating conditions, okay, close to each other, and still individually when we analyze this circuit and this circuit, and we find if you are able to match these two things, then let's try and do and see what happens.
Sir, this C4 capacitor is to lock the DC.
Yeah, DC. Because see, this DC operating point and this DC operating point was different. So that is the reason I had used that. So now, like somebody suggested, we can do that also. We can do that. It will be an efficient way of doing it. So now let's try and do that. Right, there is some is it working, or what is the error which it said?
A resistor is open.
Okay.
Load should be connected.
Load resistance is open, sir.
Okay. Let me do some connections. Okay, let me just delete all these things. Okay.
Sir, that load resistor should be connected to that output net, right? Because then the CS amplifier gain will be much reduced without that load resistor.
No, this is the load resistor now.
Okay.
Okay. So I am getting a good gain out here. This is what I am plotting. What is CD, output voltage only, right? It has not made any difference, right? So
yes, sir.
So you should try and do that in your circuits. Okay? Try to avoid unnecessary capacitive. If you are able to maintain the DC operating points close to each other, we can do that. Okay?
Yes, sir.
Okay.
Sir, why M3 and M4 are required?
Which here?
Yeah,
These.
the top PMOS and bottom.
See, I can put a 2 resistance there. Okay? I had to get the operating point out here, right?
Both are off, right? Why do we need both?
I have just inserted this, okay, just to tell you, okay, I can use MOSFETs also as resistance, mega ohms resistance in off condition.
So how does that help? So if we remove completely, what does it alter?
No. These 2 resistance will act like they are not off. Okay, you have to consider that as mega ohms resistances. So that will get my DC operating point here between VDD and ground. It is like connecting a 100 mega and 200 mega here and getting the desired voltage here. Okay. Okay. There is some advantages in RF circuits. Okay, these devices have got much lesser noise as compared to the pure resistances. Okay, so it makes sometimes it makes sense to use these kind of devices also. Okay.
Thank you.
Okay. So I intentionally put this just to give you one more option when you are designing circuits for yourself. You can use these things also. Okay.
I have a question.
Yeah.
This is affecting our first stage output. These 2 devices, MOSFET.
No, if you put in kilo ohms, it will affect. But these are off MOSFETs. They have a resistance in mega ohms. So,
But we are taking some output voltage of first stage and we are enhancing
I have
the
some
second
noise.
stage.
Can somebody mute? Who is okay? Yeah. Tell me. Let me put that slide. Common.
I have. My question is like output is like a multiples of your first stage and second stage gains, right? Because you have used a common source and a common drain.
Correct.
It means that it's just two stages of amplifiers we used for the design.
Correct.
And then what is the use of this second stage input transistors here? It acting as a resistors.
It's acting as a resistors.
Yes. Why do we really require those two resistors?
To bias the circuit. For the first circuit.
Bias? Because we already get the output from the first stage.
No. Initially, I put a capacitor, blocking capacitor there, right? Now I remove that, right? Initially, if there's a capacitor out here, then I require to bias this, to switch it on, I require R1 and R2, right?
No. This is individually when we talk about common drain.
Correct.
But when we're talking about the two stages, we don't need this setup, right?
Correct. That we
because
removed.
Already
that we showed the simulation, right? We removed those connections because the output DC level, it is not necessarily that the output DC level matches with the DC requirement here. Correct?
No, my question is like we don't need even R1, R2 when you clubbing these two, common source and common drain.
No, there could be a problem. Say for some reason, my first stage for my design requirement, the first stage, a DC operating point is only 0.5 volt, whereas the DC operating here, the requirement is 1 volt, suppose. Right? So universally, I cannot do that. For specific requirements, I can connect it. Understood, Vishwana?
Okay. Yeah, but that control we can do it by first stage itself, right?
Correct. But we see for deciding the DC operating point, and when we talk about multiple stages, there will be for each stage there will be some specific requirements. Your gain might be one target. Okay. So for that gain you might put we should try and avoid that. But if it is, there can be situations where the design requirement of each stage will be slightly different, and you might want to operate at different operating conditions. Okay. In that case, you can use the resistances, not necessarily.
Okay. Yeah. Thank you.
Sir, I have one doubt. In the LTC simulations that you have currently shown, we have removed both the capacitances, right?
Correct.
So how did that DC factor of that first output stage, CS output stage got filtered out?
No, it is not filtered. That is acting as a biasing voltage for the next stage. That's what.
Okay.
If that is matching, you can club it. That's what I said.
Okay.
Right. I was getting around 1.2 volt there, and here I required around 1.1 volt. So I just put that. Okay. Small change. Okay. So that is how we need to think when we are making multiple stages. If you are able to match that DC level, then we can do that. Okay. So that we can do that. Okay. So common drain.
Sir. So if we are biasing the second one, common drain, using the previous stage, then do we need that transistors for biasing purpose?
No, we don't require that. I have removed that connection. I had removed that connection there in the simulation.
Okay.
Right. So this is the summary of CS, CG and CD amplifiers. This is common source. You put you can put a current source on top, right? Then the gain GMVGS R0 parallel to ROC. Okay, ROC. If I am using a PMOS, this will become R0 of PMOS. Okay. Similarly, for PMOS, I can put a current source in the bottom. Right. For a common gate, you are giving a signal from the bottom. So this is the equation, and for a common drain, this is going to be the equation. Okay. So here I have an voltage gain, current gain, high input impedance, not good for high frequencies. This is For common gate, I have no current gain, I can have voltage gain. This is good for high frequency applications, and it has got low impedance, so that I can, this has got no voltage gain, and it has got current gain. You can say current gain is there, no voltage gain, but power gain is there. And the advantage of this is you can connect low load. So this becomes my final output of an op amp design. Okay, so these are the three kinds of amplifiers, important amplifiers. Okay, yeah,
Yes,
okay,
sir.
okay. Now we have something known as telescopic cascode amplifier. Okay, so you see there is one amplifier, one amp. This is nothing but an CS amplifier. On top of that, you have one more NMOS. Okay, so this acts like a CS amplifier. This here the gate is grounded, so this acts like an CG amplifier. Okay, so this is an CS amplifier. On top there is an CG amplifier. So what happens when we apply a small signal out here? GM VGS current will start flowing through this transistor. It will come here. That current, since this current will just flow through this transistor like this, and it will be available across RD. So the output will be GM VGS into RD. So the gain will be GM RD. So the gain is same as that of an common source amplifier. Anybody has got a doubt why we got this gain?
This gain, where we are accommodating M2 gain here?
There is no M2 gain here, right? Because I am applying an voltage out here. It is creating a current, okay, which is GM VGS. Okay, whatever is there happening in M2, see, this current has to, this is the final current which will go in RD also. Okay.
Okay, but
Right.
as for my understanding, example, this M1 is a common source amplifier.
This is a common
Consider
gate
M-
amplifier. Okay, this is a common gate amplifier, and for a common gate
no,
amplifier,
no.
the current gain is 1.
No, I'm talking about M1, down one.
Okay.
This is the common source amplifier. Okay, the top one act as just a load. Okay, we giving the bias voltage, and it's a transistor. We will ignore
Yeah.
that as a common gate as
Yeah,
of now.
just give me
If you consider
just
as
give
a-
me 1 minute. I'll come to that aspect also. Okay. As of now,
Okay.
as of now, we just consider this transistor. Okay, it is just passing this current to the top. Okay, because the current gain is 1. Correct? Isn't the current gain of a CG 1? Correct? For the current gain of an CG is 1, right? We just saw that, right, in CG amplifier.
Sir,
Yeah.
sir, when we apply AC signal at the common source gate, so any change in the VG, right? A small change in the VG will cause a drain of the NMOS, CMOS, common source stage का जो NMOS, that drain will also change, right?
नहीं, अगर आप यहाँ पे अप्लाई करोगे, यहाँ पे इसको एक करंट सोर्स मानोगे, राइट, द करंट विल बी GM into VGS.
Yes, sir. Yes, sir.
Okay, and this is a common gate amplifier. This has got an we are only talking about one aspect. We will talk about other aspects also. Okay, so this is as a current. This is just current gain 1. So whatever current this is trying to pull, it will just pull like this. So this total voltage gain, since I am taking from here, will be minus GM RT. Okay. Now, okay. Now, if I say what are the advantages? Okay. Now, for this transistor, when I am looking into the source of this transistor, it is seeing 1 by GM impedance. Is it okay, Jesse? Right? When I am looking from the bottom, okay, the impedance as seen into the so because this is ground here. So like I said, right, we saw 1 by GM, right, for these. Where is that? Like 1 by GM, the impedance as seen. Okay, so that is what we will see. Okay, So the gain, voltage gain will be GM into GM into 1 by GS. So there will be no voltage gain for this particular amplifier. Okay, there will be only one GM VGS current will flow, but there is no voltage gain. Okay, if there is no voltage gain for this particular amplifier from here to here, okay, there is no Miller effect. That means the capacitance, okay, will not get multiplied by the gain. So this can tackle high frequency also, right? So by inserting one common gate amplifier in between, okay, I am just transmitting here. I am just creating. I am using this as a transconductance, and I am using this as an unity current gain amplifier and passing this current here. And I am ensuring that here to here there is no voltage gain, and hence there is no Miller capacitance, and hence it can work well for higher frequencies. Is it okay with all of you? See, this is the equivalent circuit. Okay, GM V1, right? And this is the equivalent circuit of GM V2, GMB VS. Okay, and I can put R0 also here. Okay, I have not put that. Okay, if I don't put R0, this is the equivalent circuit. But finally, what has to flow in RD will be GM-VN only, right? It can get branched into 2 or 3 branches here if I put R0 also. But ultimately, the current which has to flow here will be this only, right? If I do KCL, KVL, right? So that is why the gain will be GM into RD only. Is it okay? Now, does it answer all your queries? Yeah, anybody?
Sir, I have a query.
Yeah, tell me.
The resistor transistor M2 is now on, but in saturation region. Let's forget about the Vin for now. Without, if we consider only the DC characteristics, M2 is in saturation region. So as the M1. So M2 will be acting as a sort of a resistance here, right?
No, if you see here, okay, this you are applying a source voltage here, right? Varying voltage out here.
You can't see a cursor.
You can't see my cursor?
Yes, sir.
Yeah. Here, this is acting like a common gate amplifier. I am giving a source here. Variable signal.
Sir, I can't see the cursor, sir. I am not unable to understand where you are pointing to.
All of you are not able to see?
Oh, I am able to see. We can see, sir. We can see.
Here. Okay, Sharath, to the this transistor. This transistor is a common gate amplifier, right? Here I am putting AC ground. Here I am applying the small signal. Is it okay?
I'm still unable to process how this is in a common gate configuration.
Okay, so let me.
Because the input voltage is applied to the common source part, and the current change is happening in the common source part itself. Not due to the common gate part there.
No. Okay. Let me just.
Then how? Okay.
Let me just. Okay. This is common gate configuration. Right?
I'm seeing common drain amplifier here.
This is common gate.
No, sir, I'm seeing the common drain slide. I think my network issue is there.
Okay. This is common gate. Okay. Where I am applying a signal at the in the source.
Source, yes.
Okay. So this is common source amplifier, right? This is the common source amplifier, right? I have a GM VGS R0 and R0 and if, right? If I make an Thevenin equivalent of this, it will be a voltage source, right? And a current and a resistance in series, right? So
yes,
the common the output out here can be considered as a voltage in series with a resistance. Okay. So and hence this top one will become a common gate amplifier.
Okay.
Is it okay?
Yes, now got it.
Yeah. Jaising, did I answer your query? You have wanted to know something about this?
No, sir, I didn't ask.
Achha, you didn't ask.
Okay for me. Okay for me.
Yeah. Okay. Anybody? Somebody wanted to write, and I didn't monitor who was the person. Somebody wanted to consider the gain of this also. Is that doubt clear to all of you? Here, if you see here, whatever is this current, this only will flow here, right? So by putting this transistor, we are achieving what we are achieving by putting it here is, okay, we are offering a low impedance to this output impedance here, and we are avoiding any gain at the drain of this transistor. That gain is transferred here. There is no gain out here, voltage gain here, and hence the Miller capacitance is not there. So this becomes so this is a very, very handy circuit for high circuit and high frequency applications. Okay, but it will have a high input impedance. So for antenna, I cannot connect here. Okay, but if it is for high frequency applications within VLSI circuits, okay, this is being driven by another VLSI circuit. So the Cascode is a very good choice. Is it okay with all of you?
Sir, if we output from the drain of this M1, so will we not see the same V out?
No, there will be no voltage gain there.
Okay, so we will see only the input signal there, or
we'll see only the inputs because the gain is almost 1 here. Okay, GM into the resistance as seen into the source will be 1 by GM of this.
Okay.
So 1 by GM and GM will get cancelled. So voltage gain will be around 1 only there.
Okay.
Yeah. Anybody else? No doubts? Okay. So I'll show the simulation towards the end. I'll show a simulation of this circuit also. Right. So advantages is now discussed. Okay. Now one disadvantage out here is headroom gets one transistor over the other, right? So there is lesser headroom now available. Okay, so design to ensure that these are in transistors are in saturation, your hands get tight. So you have to be careful with the value of the resistance and things like that, right? Now, if I have one transistor here and one more transistor here, and if I see the R out from here, right? The same derivation which we did for RS. Okay, now I am putting R01, okay, because this is an R01. If I put that equation, so R out will come something like this: GM2, GMB, R01, R02, right? It is approximately this is the resistance. So it is a high resistance. Okay, so if I this is R01 into R02 into GM2 plus GMB, or I can just if I neglect even GM2, it will be GM into R01 into R02, right? So this will be this will offer very high resistances when you are looking from the top. Okay, so this is the equation. Okay, so you can just try out this equation of your own also. I'll share the slide.
What is the importance of this R out?
R out. Okay, the importance is here, right? I'll tell you what is the importance. Okay, now I have a cascode amplifier. Instead of RD, I put one PMOS out here, right, with a constant current biasing circuit. Okay, if I put an VG here, right, now the when I look into the top, the resistance is R03. Okay, so the gain will be now GM1 into R03. A GM of this, and instead of RD, I will get R03. Now R03 is much higher than that of an you can keep. So it is a CS amplifier only, but the gain is there. Now instead of this structure, I put two transistors like this, right? Now if I look into here, or if I look into here, okay, the resistances will be a GM2, R01, R02, right? So for P also it will be GM R0, R01, 2. For this also it will be GM3, R0. So if I keep the GM of all these transistors close and R0, so the gain will actually these resistors looking into the top and looking into the bottom will come in parallel. So and you have a GM R01, so this will become R0 square, and a GM of this transistor also gets multiplied. So you get very, very high gain. Is it okay? So why we did that calculation? Is this circuit clear to all of you? See, it is like very high gain, means a square of the the normal gain which you get. It is actually right. It is not even twice. It is just the square. Yeah.
This is intrinsic gain. I mean, if we connect one RL, small
then,
RL,
if RL
of this,
then
it will change, right?
then RL will become the. Obviously,
Yes.
this also is not meant for to be connected to low loads. Okay, in between
Okay.
amplifiers. Finally, you should have a CD amplifier in case you require. Right? Okay.
Okay.
Okay. This is intrinsic gain. Now you will find here also 1, 2, 3, 4 transistors are stacked one over the other. So you have lesser headrooms, right? What is headroom? Actually, you have to ensure that these transistors are in saturation, right? All of them. So these voltages will become if you don't adjust the size of these transistors, it is possible that So every VDS values now 4 V. Now if I have 1.8 volt, so VDS gets distributed here. So it imposes constraints on a design, to keep these transistors in saturation. So for the telescopic, so that is the disadvantage. For that, what we have is we have something known as folded cascode amplifier, right? So here I have this a common source amplifier, and I have an PMOS being used as an common gate amplifier here, like this. So now this NMOS, it is looking into the drain of this transistor, PMOS, source of this transistor. So hence it will feel 1 by GM only impedance. So instead of putting it there, I can put it here and take the output from here. So this is now folding it by using an NMOS and PMOS. I am folding the circuit like this. That is why this name folded cascode comes, where you will find that now not many transistors here only. This will be one transistor, this will be one transistor. So only 2 transistors are one above the other. Here also only 2 transistors one above the other. So it gives me little more flexibility. It gives me more headroom to compute the like DC operating, to set the DC operating conditions. It will be easier. So that is known as folded cascode, right? So here you will have just an GM into R0 of this whatever is the load which is connected here. So if you want to, so these are some of the folded cascode configurations. So this is there in your textbook. So everywhere the gain will be same. Only thing is the way the PMOS is connected, you can have different configurations. All of them, if you see properly, so you can spend some 15 minutes on these circuits, including the derivations if it is there. It is a common source amplifier followed by a common gate amplifier. Here if you see the first stage out here is a PMOS, common source amplifier. So load is connected here. So then here this is an NMOS now here. Again here it is common gate. So the PMOS common source and an NMOS common gate amplifier. So these are different configurations. Here this is the one which we discussed in the last slide. This configuration. These are PMOS is in the first and the NMOS is in the different in the common gate configuration. So you can analyze these circuits and the gains and all. So I gave you the concept, right? So my aim is just to give you hint, and rest of the things you need to analyze from your textbooks. It will be very, very important for your examination point of view that you try to go through all the derivations which has been given in the textbook. They are simple. In case there is any doubt, you can mail it to me, and if required, I will cover it in the class in case things are not clear. But you need to do all the because not all topologies I am covering. I am covering the important ones from the design perspective. So this is about a folded cascode. Now this is folded
from Razavi we have to do the derivation.
From Razavi. So I have given the source here, right? Here like to increase the gain, these two loads are connected here, right? Simply, when two loads are connected, when you look from here, it will be R0 into R0 R1 into GM, okay, and then one GM will come from here, so it will be 2 GM R0 square by 2, okay. So the moment you connect loads like this, okay, so it increases the impedance. So this derivation which we did, right, here, right, here, I guess here, no, where is that?
Sir, one doubt.
Yeah, tell me.
So on the textbook, right, so what are the topics you cover that only we have to refer in detail, or the topics which you have not covered?
No, you got to cover everything. It's a small chapter, okay? Different configurations are there. It won't be physically possible for me to cover everything in the limited time which is given, okay? So I will cover the important circuits, other configurations also, but the principle of operation, like main concepts I have touched upon of all. What are the advantages, disadvantages, why we are using this circuit, why we are not using this circuit, everything from an practical, if you are working in the industry, these are the things you should know. I have covered, okay. The book goes into bit of theoretical aspects also, so different configurations are given there. So that is important, because for an examination point of view, some twists and turns will be there. So unless you practice those questions which is given in the textbook, okay, it will be better. So you go through that entire chapter. It is not a very big chapter, right? So if you, by solving those problems, solved problems in the given textbook also, so you will get to know more your concepts will be more clearer, right? But in case you are getting stuck for any reason, okay, feel free to mail me, and I will try to cover that in the classes, okay. So these are some of the other useful transistor pairings, like you can have two this is known as CC plus CE, okay. So it has got a higher bandwidth. So different configurations are used, okay. This is CD plus CS, okay. Instead of CS plus CD, okay, you are using CD plus CS. So because there is no gain out here, high bandwidth, it can have a high bandwidth, okay, high frequency. This will give the gain. So in the first stage there is no gain, but it will it doesn't have Miller capacitance, okay. So that is the advantage if you use in this configuration, right. This is some configuration. This is very widely used. In the last stage, we generally try and use an BJT, because that has got a higher current capacity, right. So there are other configurations also by CMOS. So this is one of the by CMOS configuration, where in the final stage you have a BJT. Before that you all have a MOSFETs, okay. So these things are also done in most of the VLSI chips, okay. So this you should know, okay. So I think with this
in the so in the previous slide, so in the when we are using a CD plus CS, so common drain is used to drive low impedance.
Yeah, no, here the purpose is different. Here we are taking an high frequency signal, and we are amplifying it. There is no requirement of a low load here. So in that particular case, we are using this configuration.
When a high frequency signal is applied at the common drain, output will be at high frequency.
Yeah, it doesn't have a Miller effect.
Output.
It doesn't have a Miller effect.
But output of the common drain will be at high frequency, and that is the input to the CS. So that will create Miller effect, right?
That will create Miller effect.
Because Q2 is the amplifying MOSFET, so its gain will be reduced again.
Yeah, correct.
So how this will benefit for high frequency?
Yeah, you have a point there. So at the input side, it will not have any effect, but in the intermediate stage, you will have an issue there. Probably you will have to use an cascode amplifier here or something like that, right? Okay, the better option would be.
But sir, if we are using cascode amplifier, then there is no need for common drain, right?
No, cascode amplifier doesn't cater for high frequency. No, it caters for it caters for high frequency.
Yes,
right?
sir.
Okay. This is one snapshot from one of the textbooks. Maybe we'll have to revisit that.
Okay, sir.
Right. So this is a picture from some other, not Razavi. It's from some other textbooks. So this is okay.
About first one is common drain plus common emitter, or that is, how can you explain again?
Pardon, which one?
The last one, a common drain plus common emitter you have given me, sir.
Yeah, common drain plus common. This is a BJT actually, right?
Yeah.
So BJTs actually can handle higher currents. So that is the reason the final stages. Okay, we can use BJTs also. Most of the technologies nowadays, they permit a certain amount of BJTs also be put in the chip.
Oh, okay. But sir, what is common emitter or common emitter?
This is common emitter, right? This is common drain and this is common emitter, right? Is it okay? So let me before we wind off, right, this is an cascode amplifier. So if I do an simulation, this is okay. I'm doing AC analysis. So let me do an okay. This is the input voltage. Let me try and plot here in between. Okay, so it has got a DC component. So let me right. It is like from 661 to 664. So 3 or 4 volt only. So there is no much voltage gain from here to here, right? Okay, because it is looking at a low impedance. But if I try to plot output out here, or I can do this also. I add plot and I move it here. So here, if you see here, the output is from 20 millivolt, right? Here it is 1 millivolt, right? Here it is around 3 millivolt voltage gain. Okay, but some super DC superimposed 664 to 661, so around 3 millivolt, whereas here we are getting a high voltage output. Is it okay with all of you? How does it now if I do an AC analysis, right? So you will find that earlier we saw around 1 megahertz for a CS amplifier, whereas this is close to around 50 megahertz. Okay, so this cascode amplifier has got a much higher bandwidth, okay, as compared to the CS amplifier, right? So all these circuits, and you can try it out doing most of these snapshots only I have used in my PDF to give you an indication of what are the resistor values which I have used. Okay, so if I talk about the transistors, length I have used everywhere on a 180, width is around 100 micro, 50 micro, of that range. Okay, so you can use the same around 100 micro, and you can recreate these circuits and learn of your own. Okay, so I think we'll call it off today. This is all for this week. Next week we'll talk about differential amplifiers.
Sanjay, I have one question.
Yeah.
This we talked about high speed amplifier.
Yeah.
What about that? I can't see your screen. Can you? share that PPT.
Yeah. Tell me.
No, simulation, LT Spice.
Okay, you want me to done this of Cascode?
Yes. That last capacitor is acting as a DC block, or it is acting as a load also?
No, DC block. I'm taking the output.
That is a part of pole creation also, right? To push your speed.
This
bandwidth.
one. This one.
Unfortunately, I cannot see your screen due to internet issue or something. But what I'm talking about, the V, wherever you have connected V out, right? There is a capacitor between the.
Yeah.
That you understood, right? Capacitor.
Yeah. That is just to block the DC. Okay, and they will create a pole. This are the load resistance and that. So you have to be careful with that values. Okay, it should be.
Yes. Where is the pole actually? Where is the first pole according to this?
I have not done it. No, it could be this side also. Okay, this also could be the first pole. Okay, because this resistance.
Can't see
the input side. Input side also there is an pole, right? Input side also you have an filter out here, right? So there is a pole here also. There is a pole here also. So you need to compute that, right?
Okay. My intention is if you reduce that C2 value, okay, will that affect our bandwidth, or it just acting as a DC blockage?
No, that actually that capacitance actually puts restrictions on the low frequencies.
C2.
Yeah. Right. Okay.
But that one we connected to the V out also as well, right? Our main output.
No. Okay. Let me just put it as an 1 micro. Okay. And run a simulation and plot output. Okay. 1 micro is good enough. It's not making any. Let me put it as an 1 nano. Okay. If I run. Okay. Still it's not making much difference. Okay, because I'm sweeping from 1 megahertz, that's the reason. Okay, let me go back here. AC instead of let me put it as 1. If I make, you see here, that is going to affect my low frequency. It's going to attenuate my low frequencies, right? If I restore it back to say I put it 100 nano, I run. So this improves this portion. Is it okay?
It's affecting our bandwidth also, right?
Yeah.
Okay. Yeah. Thank you.
Okay.
Most of the circuits we are gonna use will have capacitive load or resistive load.
No, actually, it depends on application to application, right? When I speak about digital design, most of the circuits will be driving the gate of the other transistor, which will be definitely capacitive load, right? For analog circuits, most of them are, if it is an real-time applications, okay, it could be we might be driving a sensor, or we could be driving an right, and we could drive anything, right? And
yes, sir.
So you can't really specify that for an analog circuit. The load will be, so we cater for both resistance and capacitance, right? So if you are driving another CMOS amplifier, then it will be a gate capacitance. But again, it also depends. If somebody is going to use a resistor there to bias the network, even that resistance becomes a load, right? Okay.
Yes,
so it is all for analog circuit. You can't be very, because there is no fixed requirement, right? For every circuit will have a different requirement. So accordingly it will change.
Okay, sir. Thank you, sir.
When we talk about if this is driving a normal speaker, it is a resistive load, right? So
yes.
Right, the final output is similarly if you are driving say this is going to give as an input to next amplifier stage. Okay, then it will become sometimes in analog circuits we use potentiometers to control the gain. In that case also you can consider it is a resistive load. So it depends on various application to application.
Okay.
Okay. Thanks a lot.